So welcome back to the lab. Today I'm going to talk to you about insulation and condensation. And they are related, but we've been building buildings kind of the same way for many decades at this point. And so in a lot of cases, people are basically building things just because that's the way they've been built before. But when you're building with a metal box, things are a little different. You have to go back to the engineering. Also, a lot of the people online that are showing YouTube videos of building container homes are doing so in warm environments. So I've seen some in Florida, I've seen some in Costa Rica, things like that, where it's warm, humid environments. And so you really have to kind of customize based on where you're living and what your humidity and temperature requirements are. It's not just a one-size-fits-all design. So there's a few fundamental things you have to understand in the engineering and physics. And that is, what is condensation? How does it occur? What is insulation and how does it work? Okay, so here's what we've got, is that the reason you get condensation is, for example, in your bathroom, right? Where you take a warm, steamy shower, and where does the condensation occur? On the cold mirror. Because what's happening is you've increased the humidity and the temperature of the air so that it can hold more moisture. But when it comes in contact with the cold mirror, it reaches what's called its dew point, and it will condense on the mirror. So a couple things that we need to do is control the humidity if we can. So if you're in Florida, you can't control the humidity of the outside air, so you have to take care of the surfaces. Now, in my environment, I'm going up in a cold, snowy environment, and chances are the higher humidity, in most cases, is going to be on the interior. You have to remember where your humidity comes from. If it's not outside, the humidity actually comes from our breath, our respiration, our cooking. People don't really realize that when you're cooking something like natural gas or propane, that one of the byproducts of cooking and a flame is water vapor. And so that water vapor is going into this air, and then it reaches the cold windows, or it reaches the cold metal box, and then you get condensation, which is bad because it runs down inside your wall, it condenses, you've got mold, you've got rust, and all those kind of things. So two things we can do. We can control the humidity, if we can, and we can control the temperature of the air and of the metal surface. So, all right, in our environment, if we're trying to keep the humid air, interior air, away from the metal, maybe we can do that with a vapor barrier that is between the living space and the metal. Now, in most cases, I'm not talking about the humidity on the outside. There also has to be another, like a Tyvek layer on the exterior that keeps the atmospheric moisture from getting to the cold metal. But chances are the metal won't be colder than the outside air. So that's what makes that environment for us a little bit easier. So like, let's say we had a below, like right around freezing temperature day, right? The atmospheric moisture, or the relative humidity of that air, is not going to encounter a colder metal surface. That would mean that somehow we chilled the container cabin colder than the air it was outside. Not real likely. It could happen if you had like a really cold weather and then it suddenly went warm and that kind of thing, and then the moist air could still condense to the metal box. Not real likely. I'm still going to have Tyvek out there underneath the siding before it gets to the metal, just normal practice, construction practice. But on that interior, we need to do two things if we can. Keep the metal from getting below the dew point and keep the humid interior air from getting to the container. So we have two things that we're doing on that. So if this is our container, and that we've got to have our exterior and our interior surfaces, we want to keep this interior warm air from getting to that. So what we're actually doing is putting insulation between our interior space and the metal. And we're also putting insulation between the metal container and the exterior. In our case, we've selected GPS, or graphite-filled polystyrene, because we've discovered a couple of things. There's a few other foam-type products. There's the one that sprays in. Great product, right? Forms a perfect seal to it. So it blocks your moisture vapor. Great stuff. Very expensive. You can't do it on your own. Right? And so you have to pay several $1,000s, have someone come in and spray that insulation in. Again, great for a production model if you have the money for it, and and you can do all of your insulation on the same day. So if you're working on doing some rough electric and rough plumbing and it's taking you over a period of time, then that spray foam insulation is not practical, because you call those people in once, they spray it all in one day and they're gone. So we're using GPS insulation because some of the other foam boards that are out there will have an R value of 7 or 7.5 per inch of insulation. But I've discovered that a lot of those have found there's a problem, that the loft agent, or the gas that was introduced in the foam, kind of evaporates or leaves the foam over time, and you lose R value. I saw some reports that were saying that as much as half of the R value is gone in the first year. It's also not as good in the cold environment. So that's one of the reasons I did not select using some of those foam board, or like a solid board insulation foam. Instead, going with GPS, it looks like black polystyrene, and it's about only an R value of 5 per inch, but it doesn't degrade with time, and it's better at cold temperature. So that's what I've selected. 1 inch on the interior, 2 inches on the exterior. Again, with that concept of not letting the metal get as cold as it could be. So that's putting the 2 inches of insulation on the outside. And then also not letting that moist air get to the metal is done with another vapor barrier on the interior. So I found another insulation out there that has a lot of hype around it, but I don't see a lot of really good data. It's about 1/4 inch thick. It's foil-backed foam. Not the bubble wrap stuff, but it's actually like a foam layer, like white foam, and it has foil backing on both sides. It is waterproof because that foil backing is as a low permeability, but I don't believe the R value they're talking about on it. It also provides a radiative insulation factor, which is great. Remember, there's 3 ways that heat is transmitted through things. You have your conduction. Conduction is through a solid material, usually, like metal. So we have conduction in the container, where if there is a way that the heat can get to the metal, it'll travel through the metal and then it will escape some other place. Remember, heat always moves from a place of higher temperature to lower temperature. If there is no difference, there is no thermal transfer. There is no heat transfer because there is no delta T, or difference in temperature. So in the example in our container is that we've taken a 40-foot container, cut it in half, joined the 2 halves together. So that's kind of this diagram here. So I'm only insulating the exterior surfaces of this whole thing, because the interior shared wall is one container up against another container. Theoretically, it's 68 degrees or so on both sides, so there shouldn't be much thermal transfer in there. But by conduction through the metal, it could escape into the metal and go to the outside. So that is conduction. So convection is when the thermal transfer is through some kind of fluid. A lot of people think of fluid of being like water, but air is also a fluid. And so your convection oven is a fan blowing that 350-degree air around the oven, and you get a much higher efficiency of thermal transfer when you're moving that fluid over the object that you're studying. So in our case, we have convection. Right, is that you've increased the temperature, or you're maintaining the temperature on the interior. It's a cold wintry day on the outside. The air is blowing over that container. So it's worst case conditions. It's trying to strip that heat away. And then the third way is by radiation. And radiation is more of that line of sight transmission of heat energy, and that you can help prevent that through reflective surfaces. The more the better. So like on spacecraft, we used to use multi-layer insulation. It was aluminized Kapton, and with every layer, the only way to transmit that heat energy is by reflecting that energy into the first surface. Then it has to reflect that to the next surface, be absorbed by the next surface, transmit it again. And so if you decrease the emissivity and you decrease increase the reflectivity, shiny stuff, it doesn't transmit it by radiation. So that foil-backed insulation layer that's in there does help with a little bit of a radiative transfer, so that if there is any heat, it gets reflected back into the space, and then it also doesn't reflect much onto the next surface. So we are looking at doing kind of a multi-layer thing here, where here in the middle is our metal. And then this green layer right in here, hopefully you can see that. This is on the interior, where we have 1 inch of insulation, of that GPS insulation, right? So between the GPS insulation and the metal, is that foil-backed foam layer. So it doesn't let any of the humidity get to the metal. And on the exterior, we have this 2 inches of GPS insulation, again, trying to prevent the cold from getting to the metal. So here's something about relative humidity, is that there is no one temperature that moisture condenses. What it is it's a relative factor. And I looked up a few of the numbers for that to kind of see roughly what temperature do I have to maintain. And if we assume a relative humidity of 50%, and I know in Florida, Texas, East Coast, or something like that, that's a pretty low number. But up in the mountains, or in an interior space, that's probably pretty safe. So 50% humidity, the dew point will be 50 degrees Fahrenheit. Just kind of an easy one for me to remember. So if you've got a relative humidity, 50%, and the dew point's 50 degrees, I need to keep that container from getting to 50 degrees. If I assume my exterior temperature is around freezing, then I can probably keep this with about a 20 degree delta T across that 2 inches, or R10 here. There's also one more factor that I found. Another product out there. I'm going to try it out and test it. We'll see what we come up with. It is a paint additive, and it's kind of a cool concept that they made these microspheres out of a ceramic material, and they are filled with vacuum. I don't know if you can fill something with the absence of something, but they are vacuum-filled microspheres of ceramic. And if you can picture that Yeti or that Hydro Flask, and it is a vacuum, basically between 2 layers of a shiny stainless steel. So now picture, you've got your warm exterior of the flask, and you have your ice cold tea on the inside, is that heat is going into that first layer of stainless steel, and what it's trying to do is transmit that across. It has 3 methods. It doesn't have much conduction because there's no metal path getting across. It doesn't have convection because there's no air or liquid between the 2 layers. So the only thing it has is radiation. If you make those 2 surfaces shiny and you have this void filled with a vacuum, there's no way for that heat to go across except for by radiation. And that's why ice stays frozen in a Hydro Flask all day. So the concept with that paint additive is that those microspheres are vacuum filled. You put it into a primer or some kind of liquid media carrier. You paint it on the walls. You put enough layers up there and you build up this vacuum surface. So these are the corrugations of the metal here. And then you paint enough layers on here, obviously not to scale because this metal is only about 60 thousandths thick, and I'm just not able to make circles small enough to reflect microspheres. But you can see here what you've got is the 1 inch of insulation. Here you have the radiative and moisture-proof boundary layer, and then this paint additive on here, keeping one more layer so that this cannot be 50 degrees in contact with our moist, humid air on the inside. And then 2 inches of insulation on the outside, keeping it warm, and our Tyvek, and then our traditional siding out here. In most cases, our siding is either going to be like a roofing product, like a standing seam roof, we're going to use it as a siding, or a concrete siding, like a hardy plank or hardy siding, those kind of things. So that'll be our last surface out here. But we do have that Tyvek layer to keep any of that moisture away from the rest of this stack up. So you really need to study your particular environment. So if you're designing a metal shipping container house that's in Joshua Tree, the desert here in California, relative humidities are going to be nil, right? But they have thunderstorms, so so you will get some brief excursions of higher humidity. But you're going to have huge delta T's, or difference in temperature from interior to exterior. In that case, you might be air conditioning, well, you will be air conditioning your interior, have it really hot on the outside, and so you have to think about where is the moist layer. So it's not one size fits all. It's not that you can put the same shipping container cabin anywhere. Now, is this much different than building a regular home? Because a regular home has these wood stud bays, right? You fill the stud bays with an insulation and you put your moisture layer on normally the warm side of that wall. Yeah, it's a lot different. One thing in doing this construction is we don't have thermal bridging. In a normal 2x4 stud bay, every one of those 2x4s is a thermal bridge. It's just wood, and it will transmit that heat across that interface every 16 inches. And you think, that's not that much. But think about this. A wood stud is 1.5 inches. Those studs are about every 16 inches. So basically you have about 10% of your wall is solid wood and 90% of your wall is insulation. And so you're only getting that, that R value, you're not getting R19 across your entire wall. You're getting R19 on 90% of your wall and only, the R of solid wood on 10% of that wall. So it averages out numerically. This has no studs. There's no thermal bridging. So the only way that the heat can move from the interior to the exterior is through convection, basically, and this is all insulation. I only have screws, and the screws are only on the high points. So there'll be a screw here that goes through and picks up this corrugation, and then the screws on this side go through and they screw into this metal corrugation. So the screws are a very small percentage of the area for our conduction across that. So you get really great insulation values because it's 100% of the wall is insulation. The only framing that we really have is around the doors and windows, and it's only enough framing really to turn the mounting surface, because you can picture you're taking a window that has a nailing flange like this, and you're putting it up against a whole bunch of corrugations, so you can't really do that too well. So what you do is you put angle iron in there, turn that mounting surface so that now you have a wood frame. Now, most people that are doing these container homes online are showing the container on the exterior, and that method would not work at all. It would leak. You'd have to weld all that stuff in. We're not doing any welding, and we're very little. And the way we're getting away with that is we're doing all of our waterproofing on the exterior in a very traditional way. Tyvek wrapped around the windows and keeping that moisture from getting inside the wall, because all of our insulation is on the exterior. If your container is the thing that's exposed to the outside air, then that has to be your waterproof boundary right there at the container. And then the container is matching the exterior temperature of your environment. In Florida, who cares? It's 70 degrees. Winter, summer, great, right? So your metal surface is 70, who cares? You're in Joshua Tree, it's 120. You're in the mountains, it's 30 degrees. So then you care and you don't want your shipping container exposed to that exterior necessarily. The other benefit that I've seen is that most people are putting that insulation all on the interior. Your container's only 8 feet wide. As you add insulation to it, that container that's already small is getting smaller. So that's another reason why I was putting 1 inch of insulation on the interior. Somebody might ask, why don't you put all the insulation on the exterior? I think that's a possibility. It's harder to find screws that are 3.5 inches long, 4 inches long, that are self-tapping, self-drilling, that will go into these corrugations. So I think that would be another challenge if I'm trying to put all my insulation on the exterior. And also I just didn't want that cold metal surface, even if it's like 55 degrees, I didn't want it to be an exposed surface inside the container. So that's a brief discussion here on insulation and condensation in a metal structure. So we'll see how some of that goes. I want to do some testing on that paint additive. I've got a plan for my class that we're going to cut out some samples of the corrugated metal and have some that is treated and some that is untreated with that paint additive, put them in a freezer, get them to the same temperature, and measure the change in temperature over time and the same environment. And that will also tell us then how much those track, how much the conductivity is in those, and that will tell us a little bit about how we would be preventing or encouraging condensation on that additive. You add about 1 pound of the paint additive per gallon of paint. So we'll see if it was worth it. Had to try it out and get a few pounds of that. See how it works. All right, so I'll take you out to the container here in the other videos so that you can see what all this stuff looks like when it's put together. But I figured I needed to come inside the classroom and kind of cover some of the physics and math behind it. See you next time.